All right, now welcome back. So this is the second part of the normality uh, checks we talked about in previous class, where we talk about one of the assumption of parametric test. So we want to look at it practically now. Here we have understood how it works theoretically, just to understand the background of what we are talking about. So now we want to look at it practically now. So we want to install our library called tidyverse. Then we install also base test R. So these two will be useful for us to in this analysis, in this test. So we just run two together, right? So if you have not installed, can do that installation before we go further. All right. Don't mind the warning, okay? Just let's continue. Now, from this base 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 test R, we are going to use a function from there called distribution normal. This distribution normal will help us to create a normal distribution variable or column. All right, we call it data, just to start to test how a normal data should look like normally. Okay, so we want to create a 100 number of observation, but it will be just be one column, right? So the mean is 0 and the SD standard deviation is 1. So if you run this line of code, now the data is created, so we have data. This data is just one column called n. So if you want to view the data, you can just say, if we describe it, we can even glimpse it. If you glimpse data, of course, data as usual, we have a num, is number, okay, 1. The 1 means one column, 100 means observation. All right. So these are the data we have inside. Okay. If you want to see the first 5, you can just press F. Data. Right. So you can see the first 5. So this is the first 5. The first 6 rather. Sorry, first 6. So this is what we have there. Data. All right. So this is what we created. We call it we call it data. Okay. As data set name. That's only one column. All right. So we can find the first thing we want to look at. I want to look at the histogram of this data. All right. Last time I talked about so many things. If you do, I didn't mention histogram there, but it's one of the things that we use to check the normality of data as well. All right. So it's very important too. So let's mention it here and see. If we run the histogram data, you can see this data shows a normal distribution. You can see here from 0 here to the left side, you can see the shape of the histogram. It shows the shape of it's like a bell shape. Okay, when you talk about density plot, which we talked about previously in our skewness of data, we saw that because skewness does not only based on density plot we showed at that time. It's also based on histogram. Okay, both of them have almost the same structure when it comes to data distribution. Okay, they can both be left skew and right skew. All right. So now, but this one we showed the other time. Okay, this one. Okay. So for this data now is normally distributed now. Okay, it has a perfect bell shape or symmetrical bell shape. Okay, so that is how data should be symmetrically, or if you assume a normal distribution, it should look like this. Okay, please take note of that, and that's just a simple plot to show the data distribution. So we are going to create a histogram together with a bell shape now. So we can just run this line now, pass our data in, create histogram, pass our data in. If frequency false, the mean frequency will be false. This particular line is supposed to be frequency, going to false. Then we put an heading, okay, so that you can just describe the data. They put the density line here, like this density line created here, put on top of it. That's what we are trying to do now. Make it thicker to line width. This line width thicker. We make the color of the line red, right? So we just want to do now. Let's just plot this and see what I'm talking about. You see now? So this is what I've done before, but we are now combine together the density and the data. Now. So we have the bell shape here, which is perfect now, and they also perfect histogram. So this is called normally distributed data. Okay, the data should look like. Okay, this data was created actually. This particular one was curated, so it's not something that we to collect for ourselves. You can see that we created it using. You can also use a Q norm to create data. Okay, sort of using a distribution normal function. All right. So now let's further look at a QQ plots as well to describe data and see how it look like. Let's say we run QQ plot for example. Like QQ plot, you can see it's normal. It's on the every lines on the line. Can you see? So nothing was outside the line, which means this data is normally distributed. All right. So take note of that. But if you also check the box plot on the box plot of this, just pass data in box plot. Okay, because you have only one column, that's why you just use data straight. If not, you can say data dollar number of column. I mean the column name, right? So just run this line. I say box plot is perfect. Okay, it's in this particular mean is in the center. Okay, it's in the median. The mean is equal to median. That's what it means. This mean equal to median. It's in center here, and it's equal to 0. That's what we learn theoretically. Don't forget that. All right. I said before that it may possibly not to be equal to 0, but it must be equal to median. Okay, take note of that. So now this is just a sample of a normal distributed data. Okay. So you can also test this data by using statistical test called Shapiro test to check the normality. To be able to do that data to see. Okay. So because if you want to test Shapiro test, for example, you can just pass in data here. Say Shapiro test. Okay, data, because we have only one data, only one column there. So which means this data must not be significant. If it does, it means it's not normally distributed. Okay, that is concept of Shapiro testing and the Levin test. All right. Levin test is for the to check the variance or the homogeneity of variance. So we'll do that later. But at least you must understand that here, when you test numerically here, it must not be significant. So if it's significant, then it means that it does not follow normality assumption. Right? So which means the test fails. The test fails. So for you to test the test to pass, it must not be significant, which means it must not be greater than 0.05, which is our threshold, p value threshold, validity value. So it must be less than. So it must be. So if it's greater than 0.05, it means it passes. But if it's less than 0.05, it means that it fails. So what that means is significant. So it must not be significant for us to pass the assumption. So let's look at let's run this line and look at what I'm talking about. You can see p equal to 1, which means this p is not significant. Shapiro weak for normality test is not significant, which means it passed the normality test assumption. It's passed. But if it's less than 0.05, it means it failed, which means significant. So you must understand this before we go further. So because I'm going to do more of this Shapiro testing later in different areas, so it's good to understand the concept first at this elementary level. So now we want to now use normal data from our R. So we have what they call empty cars. Empty cars is a data set in R, right? So I think I've described that before. You can just type here and look at empty cars. Okay, just you want to query empty cars, you want to know what is inside empty cars. So it's showing here, it's a motor trend car road test. All right, the data was extracted from the 1994 Motor Trend US magazine and comprises of fuel consumption and 10 aspects of automobile design and performance for 32 automobiles. All right, so here we have variables here. The data frame with 32 observations on 11 numeric variables. So we have 32 rows and 11 columns. That's what it means. So we have MPG, which is miles per gallon. We have a seal, which is number of cylinders. we have this displacement, we have HP, which horsepower, we have draft, access ratio, the angle ratio, we have weight, which is WT, and the rest of them. So this is our data set we have here. So you understand that you can look at more of the data if you want. But that's called MTCAS. So it's a commonly used data in R to perform some analysis and some tests to learn how to work with data. So we're going to use it here to test, right? So now from the data set, now we want to look at it. You can first describe it first. Let's say we describe it. Let's glimpse it as usual, and glimpse MTCAS. Okay, MTCAS. You run this line of colors. We want to glimpse it. Right, that's what we have. Okay. Okay, we have 32 rows, 11 columns. Okay, you can get MPG, what is inside MPG, cylinder, displacement, horsepower, and the rest of them. That's what we have. Okay. So we have some categorical variable. Okay, one of them is seal, cylinder. Okay, cylinder is categorical variable. Okay, number of cylinders. So we have 6, 4. Categorical variable could be numbers and could be string or character. So that numbers are not, it's not countable numbers. Don't forget. Yes, not the countable numbers. Okay, just a repeated number. So we have 6s, we have 4, we have 6, we have 8. So it's basically 3, 6, 4, and 8. That is 3 levels. It has 3 groups. This particular one has 3 groups. Don't forget. This particular variable has 3 groups. So it have 6, 8, and 4. So that is it. And we also have another category we call VS. VS means vehicle engine. It can be 0 is V is shaped. It's V shaped, that is for 0, and 1 is straight. So this VS, all right. This is a categorical variable. Don't forget. It has 2 groups, 0 and 1, right? We also have AM. It's also a categorical variable, right? We have 0 for it's called transmission, 0 for automatic and 1 for manual, right? So you can see that we have 2 groups, and we have 0 and 1. So they are categorical variable, even though you can see that they are this is their name. You can only put this one here for 0 and this one here for 1 directly. So which means they are not just they are not numbers. Okay, they are just represented as 0 and 1. So take note of that. You can have categorical variable, for example, male and female. You can use 0 for male, 1 for female, whichever one you prefer. So they are categorical variable, but they are represented in numbers, but they are not a countable number. So take note of that. All right, so if that is clear, let's continue from there and look at how to test normality using our data called MTCAS. We already see what is inside MTCAS, right? So we want to look at one of the variables called HP. Okay, so we want to create a histogram for HP, for example. You can say HP histogram. So don't forget to create to access any variable or any column. You use the name of the column, name of the data set, the variable name. Don't forget that. I think we have done that several times, so that shouldn't be an issue now. So of course I can attach the table name. This one I can attach it, then use HP directly as usual. All right, that to make our work faster as well. But let's just go with this first and see what I'm talking about. So look at this. This is a right skew data. Right skew, okay? This is right skew. Right skew. Take note of that. If you plot for example, let's plot the density line. Density for this, for example. You can see, you understand that let's just say we want to plot the density for this guy, okay, and see how it look like in a right skew manner, right, or right skew mode. Okay, so let's just say, okay, we want to put here density line. Okay, MTCAS $HP. Let's see how it look like. Can you see? See that's a right skew. So it's a right skew, okay? That's it. Right skew. So take note of that. So that's what we learned the other time, right? So it could be a density plot, which I showed you before in skewness. It could also be histogram. So it doesn't matter. They are both used. Okay. So let's go now. I want to put in this histogram now. We are working on. So let's just remove this. I don't need it now for now. Okay. I'm just trying to test. All right. So it's not needed for now. All right. So I can put it here for this negatively skewed one to test, okay, for WT later. All right, so let's just keep it there. I'm going to use that later. So I want to run this together, okay, because I've run the histogram here, this histogram here, okay, which is a right skew, and I want to show that our mean and mode. Okay, so now we want to create a line here called mean line and mode and the median line. Okay, you call it half line. We also say vertical equals to mean. Empty car is vertical line now. Empty cars horsepower. Want to create a line based on that. We want to create the mean of this variable HP. Color is red, and the line width is 2. Thickness. Okay. We want to create a median line also, and want to make it color blue and the line width 2. So if you create it on this histogram now, let's run this line. We run this 3 lines together, for example. We run it together. You can see here our red is mean. Okay, the mean is red, and the median is blue. Okay, so in this case now you can see that the mean is more than the median, okay, greater than the median. So this is not correct actually. Okay, this is because this is what is called positively skewed data. Okay, or right skewed, because whenever the mean is more than the median, it is called right skewed data. So take note of that. That's what I showed us in that time in the previous analysis we did. I mean, based on introduction we have now. So I don't want to be going there again. So you can go back there to test, so you need to check. And also, for example of a left skew data is practically is when you are when you one of the variables is called WT here. If I run this line WT here, you see, you can see here. So it means it is a negatively skewed, right? So you can run the same thing here for the one for half line here, right? Run this line. So you can see that it's negatively skewed here, and the median, the mean is now lower than the median. Okay, this is the red mean. It's now smaller than the median. So which make it to be what? Negatively skewed data. All right. So take note of that. We also have a MPG. MPG should be okay. Let's see how MPG looks like. Okay, MPG is there too. Let's say we run this line. MPG is closer to normal distribution. Closer, just only here. Closer. So let's look at it here by changing this one here to MPG. Right? MPG here. MPG here to see how it looks like. So if I run this now together, okay, so it's also you can see that it's skewed also, right? The red is more than the mean is more than the median, all right? So take note of that. All right, so that is that for that. So you can log it sometimes to transform it, and it's to transform the skew data. It's good to log it, right? So probably if we log it, maybe it will improve the distribution of the data. For example, in this histogram now, let me see if I log this MPG now. Let me see if I log this density log. Let's say log bracket here. Close. Alright, so try to see if if I log this particular MPG, maybe it will improve the plot. Let's see. So does also improve this histogram? What of the box plot? Let's look at the box plot. MPG box plot. Empty cars dollar MPG. I think the box plot. Box plot is not too bad actually, but it's skewed. I think it's skewed. It's kind of skewed. Same thing. I've checked up box plot for the rest we did just now. Okay, you can see the skew. You also see the skewness we observe in those ones. So, for example, if I check box plot for this one now, let's say if you change to, if you say box plot, empty cars. Let's say dollar HP. Okay, run this line. Can you see that's one outlier here? Can you see one outlier is here? So, but you can see it's positively skewed. Can you see up here? So the other time we just horizontally arrange it, but this time around you can see it vertically. You can see it's skewed. This line is bigger, it's more than this line, so that's a positive skew. Okay, let's look at the second one here. Box plot. You can see box plot here also. Box plot for WT. Box plot. Empty cars dollar WT. So if I run this line of code, where is it? That's empty cars. Okay, sorry, empty cars. Empty cars. Alright, so I run this line. So you can see this one is also skewed. Two outliers here, but you can see that this one is more than this. And see where this one is closer to this place than this one is long. Yeah, it's from here to here. So that is equal negatively skewed. Okay. So that is how to discover that. So let's move forward, and we just run. You can also run QQ plots of that same. We are talking about not QQ plot of WT, for example. You see how it looks like. You can see outlier outside. You can see some things out. Okay, some very perfect. So apart from this particular, you can also test for normal distribution. Okay, you can test for normal distribution statistically by using Shapiro test, which we did the other time, to see how it works. So let's say we want to test empty car WT for Shapiro test and run this line of code. Shapiro showed that the test passed 0.09 is more than 0.05, which means Shapiro test passed. So you can, but we have to compare very well with graphical output. So even though test passed, let's see HP also. HP is very close, 0.048, which approximates 0.05. You can just apply 0.05, which means it also seem to pass the test of significant. But let's see MPG. That one passed accurately. So 0.122 is very much more than 0.05. So if significant, no normal distribution, normality failed, but it is not significant, which means normal distribution test passed. So it's only, I think, the only HP that is having issue. HP having three outliers or two outliers. So that is how we look at it, normality check graphically. So later we see how to undo them later, but at least later we just need to describe how normality, you have to test your data if it passes normality test or not. So understanding that the Shapiro test is very powerful, it's very important to confirm and conclude if your test passed normality test or not. So you can confirm using a Shapiro test. Okay, there are other tests that you can use, but Shapiro is the most popular one. Okay, which we have applied just now. So I think we stop this one here for now, and we'll continue from there in the next class. Thank you so much for listening. I will see you in the next class.